Welcome. Please, everybody, close your laptops. I hope everybody got a handout because of St. Patrick's Day. They are in green. In Germany, St. Patrick's Day is today. Okay, so last time we talked about the bias-variance trade-off, which I consider one of the most important topics in machine learning and data science. It's really a topic that comes from statistics. This is something that statisticians basically first derived. And the idea was the following. Last time we basically came up with all these, and I brought it up here just to make this faster. We basically looked at the expected test error of an algorithm A, where we basically say, we integrate out any possible training data D, and then we look at a test point X with label Y, and we say, what's the probability that we draw this train data D, then this test pair X and Y, and then given that, what's the error that we get, right? And if you integrate out all of them, that's exactly the expected error of that algorithm from that data distribution for a given training data set size. And so we looked at that error. This is this term here on the left. And this is just, basically a squared error here, expectation of a squared error. But then we looked at this a little bit more closely and decomposed this error. And we found something pretty amazing. That this term decomposes into three very interpretable terms, right? And let me just, go through every single one of these one more time. So the first one is the variance, right? The variance basically says, how much do my classifiers vary, right? If I take, would basically, in some sense, a classifier is a random variable, right? I'm drawing a classifier, which is basically the process is I draw a data set and then I train a classifier. So I can also view it as drawing a classifier. So if I draw various classifiers, how much do they vary from the mean, right? This is exactly the variance of these classifiers. So, it's amazing, right? Like if you just think about this for a second, that this square term decomposes in the sum of three different quadratic terms. And each one of these is beautifully interpretable, right? So this is going to help us a lot when we try to make machine learning work in practice. So please really pay attention to this and make sure you understand every single one of them. So one more time, this basically says how much do the classifiers itself vary, right? This here is the noise. So here the important thing to realize is that when we minimize the square loss, which was the assumption we made here, the square loss is minimized at the average label. So the average label is exactly this guy here, right? So this is the expected label in this case, right? So what our entire algorithm is trying to do is trying to find a classifier that reliably, for a certain X, outputs Y bar. Right? That is the goal of the machine learning classifier. And what the noise is measuring, saying that even if I'm 100% correct, right, every time I'm hitting exactly Y bar, right, I still have some error. Because the data points don't actually always have the expected label, right? They can vary themselves. And that's this term here, right? So it's exactly the variance across the label. Okay? Any questions about the noise or about the variance? Yeah?
So, intuitively, as you get a bigger data set, your variance should go down. So, as it gets larger, your H of D should approach H average, right?
So that's exactly right, yeah.
But isn't H average weighted by just an average of all of your functions weighted by how likely it is you are to get that data set? And isn't having a bigger data set less likely? So why does increasing your data set make you...
Oh, I see. So this average is, they all have the same data set size. In this case, basically, I didn't actually go into data set sizes.
Oh,
right? But it's still the case if you would have a very large data set, you would, in the typical case, actually, your H would approach this H bar.
Okay.
Right? So then actually, so that's exactly right. Here's actually why. I can tell you it's very simple, right? So in some sense, this captures the variance of the data as well, right? So if I would actually sample, let's say I'm sampling 1 billion data points, right? And then I'm sampling another 1 billion data points, right? Well, these two sets won't be very different, right? Does that make sense? It would be extremely unlikely that the first 1 billion data points are completely, very, very, very different than the next 1 billion data points, right? It would be 1 billion times I'm drawing from this corner of the space, and here 1 billion times I'm drawing from this corner of the space. It's not going to happen, right? So when the data sets are small, then actually if you draw many data, different data sets, they will vary quite a lot. But as your data set gets very, very large, the next time you draw a different data set, you will basically get the same one. Right? Does that make sense? So that actually, so ultimately what that tells us is as my data set becomes large, this becomes very small, right? Because my classifiers won't vary very much anymore. Right? Very good point, very good point. Okay, so then we have the noise and then we have the bias. So what does the bias say? The bias says, now we take the expectation, this is independent of the label y and independent of the training data set. This says basically, take away, assume we actually get the average classifier, right? We basically converge to this, right? How much error does that still make, right? So even the expected classifier, right, is not good at hitting the label it's trying to aim for, right? And that's because we make some assumption that is not true in the data. Right? So no matter how much data we have, here we averaged over an infinitely many classifiers, right? So infinite amount of data, right? Still, we are not hitting the expected label of the data points. And why is that? Because, for example, we assume that the data is linearly separable when it's really not, or something like this, right? So it's really important to kind of, it's really beautiful how these three different terms capture completely different aspects of our algorithm and of our data. Does anyone have an idea how to reduce, for example, noise? Right? So this is kind of, these two are down in the algorithm. But what do we do about the noise term? Any idea? Sorry? It's irreducible? It's a pessimistic view? Yeah?
Filter out outliers.
Filter out outliers? Sure. So if you basically say some terms, but then you actually change the data distribution, right? So you would actually say you change the distribution to some p prime, but you say we exclude certain points, right? Data cleaning, yeah. Add more features, right? So that's actually a really good one, right? So y bar here is a function of x, right? So x basically describes your data. That's really important. It's like if you try to predict the price of a house, right? Well, if you only have 3 features, number of bedrooms, number of bathrooms, and square footage, right? Well, then actually, the amount of just based on these features for any given house, right, there could be a large distribution of prices, right? But if you have much more fine-grained features, then hopefully eventually you're actually going to pick up the nuances of the pricing, right, and the variance will go down. Right? So this is not something that's just given to you. You as a data scientist can influence each one of these terms. Yeah?
I'm just going to say you can also get more data to reduce noise.
No.
Oh, you can?
No, you cannot, right? The variance does not change, right? More data does not make any difference. This is the expectation over distribution. There's no notion of your data set D. Right?
Are you more likely to pull out things closer to the mean, though, than...
No, this is expected value, right? It's in expectation. This has really nothing to do with how large your data set is. This is really something about the distribution. But be careful, the distribution is over the space, described by your features. Right? So that's the one thing under your control, right? The feature space itself. Okay, yeah?
So if you have more features, aren't you afraid of overfitting sometimes?
Right, so here comes the interesting bit, right? So what he's saying is, if I add more features, right? And I make this here smaller, right? I may make this one larger, right? And that's exactly what's happening. It's a little like whack-a-mole, right? You know this game whack-a-mole? I don't, but it's kind of like that. So you press one down and then something else comes up. I think that's what I'm picturing. So that's exactly the problem, right? So it's very, very hard. The moment you bring one down to 0 or something, right, the other one's going to go up, right? There's always a trade-off, and that's exactly why we call it the bias-variance trade-off, right? The beauty of it is, and this is where your power comes in, the realization that each one of these terms is quadratic, right? So one will always dominate the others, right, or very likely. So what you want to find is an equilibrium, right? So it could very easily be that the whole thing is large because bias is massive, and these two are very, very small, right? Then you have the chance, because it's quadratic, to reduce bias a lot and only make these two go up a little bit, right? And that's basically, that's usually actually what you're trading off is variance and bias. This is the two, right? So if you get one down, the other one goes up, but it doesn't have to go up by the same amount. And that's the skill that you have to learn as a data scientist. And we will talk about this exactly in the next couple of lectures. So, no more questions. One thing I want to show you is the project that's coming out today. Oh, I hear excitement. So, good stuff. So here is this it? Is this connected to the kernel? Oh, that was connected to the kernel. Okay. Okay, 1 second. Bias-variance. Here we go. Okay, so this is the prototype. So this is actually not exactly what you will see. So 1 second. Is this running? Okay, good. So here's what we do. We draw a data set. So what I want to show you is that the error is the sum of these terms. And this is in some sense what you're going to test in this project, right? To really kind of see, like, that the error really decomposes into these three terms, and then how large is each one of these three terms as we vary the settings of a classifier. So please pay good attention. You only have 7 days to complete this project. So here's the key. So what we do this time is we draw our data from a very specific distribution P that we know, right? So in this case, we are playing God, right? So we know the data distribution, which is typically not the case. But by doing this, we actually have control of each one of these terms. We can compute them very, very, to arbitrary precision. So here's what we do. We basically draw, I have two Gaussian distributions, the red one and the blue one. And I say all the blue points are +1 and all the red ones are -1. I believe that's the labeling. Or 0, 1, I don't remember. And so now we draw a certain number of points. And the first thing is, if you know these distributions, right, then you could actually use the Bayes optimal classifier, right? And the Bayes optimal classifier gives you predictions. And these points that are highlighted here with these gray circles are the ones that the Bayes optimal classifier would get wrong, right? So because there's an overlap, for example, here this is a blue point, but it's much, much more likely that it's actually red based on its location. So the Bayes optimal classifier would say that this point is red, despite that it's actually blue, right? And in fact, in this case, it makes a 9.7% error, right? So this is basically the overlap between these two distributions. And that's, can anyone tell me what that measures? Of these three terms? The noise, right? That's exactly the noise, right? So that's the stuff you can never ever get right, right? So that's basically, the expected label here would basically be red, right? But actually, it turns out it's blue, right? So you have no chance, you can't possibly get this right, right? Based on this two-dimensional representation. Okay, and so then what we do, and I'm gonna quickly scroll this by that you don't see the solution. What's happening here? I know people are going to watch it on the video in slow motion. Oh, I see. Okay, wait 1 second. I didn't save. So 1 second, I have to save one more time. Okay, so let me just tell you what I'm doing. It is still running. So here's what I'm doing. I take this data set. So here's okay. So now you can see it's running. So basically what I'm doing is initially I draw a lot of data from this data set, and then basically what you have to implement in the project is a term to actually compute bias, compute variance, and compute the noise, right? And then actually sum these up. And the way we estimate these is by sampling. So let me first show you the examples. So the classifier that we're using here is actually just a linear classifier that's kernelized. So kernelized, we haven't done this yet. We will do it in 2 lectures. So it's basically just to make, put linear classifiers on steroid and make them really, really powerful. So we need to do this because otherwise they're too simple. So don't worry about it for now. It's just, for all you means just a linear classifier, and we just take the data and project it into some other space where data is always linearly separable. And so then we have a regularizer. And so this regularizer lambda is set to 2 to the x. So as we go to the right, basically, we have more regularization. Okay? And so if we have more and more regularization, what are we doing? We are forcing the classifier to be simpler and simpler. Right? So if you regularize a lot, at some point we just get the all-zero classifier. Right? If we here the regularizer is 2 to the minus 6, that's very, very tiny. And so here's what's happening. That's the only thing we are changing. So we are changing the regularizer, so basically from very, very small to very large. And one thing you can see here, so basically the red line here is the bias, the black line is the variance, and the green line is the noise of the data. And if we add these 3 up, right, then we get the dotted line. And the dotted line is very, very close to the blue line, and the blue line is the actual error we are making, right? And the reason they are not exactly the same is because I set it up so it actually runs pretty fast, because you guys need to run this on Vocarium. So the way we actually estimate the bias and the variance here is by actually, for example, the variance, what you do is you learn 100 classifiers, right? And then you basically compute the average versus the average classifier, and then you compute the variance from these 100 classifiers. It would be a lot more accurate if you would train 1,000 classifiers, but it would take 10 times longer, right? So, okay, and similarly, we approximate the bias, and similarly, we approximate the noise. Okay, and so here you see some very, very beautiful trends. So the first, unfortunately, this box is right over this blue line, but you see something very, very nice that, you can really see how these 2 lines dancing around each other. And so, they're basically the same thing up to the approximation error that we get because we sample only 100 functions. And so the second trend you see, and that's also very beautiful, is that the bias, here the red line, right? As we regularize more, the bias goes up, right? So the portion of the error that is explained by the bias gets larger and larger as we regularize more, right? So basically what happens here is that the model is too simple, right? And that is why we have this large error, right? So, a huge portion of that error is basically the area up to the red line. Does the figure make sense to everybody? Is there any questions about the figure? Yeah? Yes, you can absolutely have this. You can, and that's not good. So that's called a terrible classifier. I think that's a technical term. So in this case, you don't see this, right? Because we're trying to trade these 2 off, right? So basically, if you make the wrong assumption about the data, and then you have a high variance classifier, right? So there's little value in going. Usually, you try to avoid these situations. I will show you in a minute how to recognize this. Okay, so basically, the second one is variance. And one thing you see, variance is very high here, right? So what's happening here? Here, the classifier is not regularized. And so a large proportion of the error that it's making on the test set, right, can be explained by the fact that it's essentially memorizing the training set. Right? And that's why there's so much variance across the different classifiers. Right? So we train 100 classifiers, compute how much they vary. They vary a lot because each one overfitted to the very specific training set that it was trained on. Okay, so does that make sense? So that's the failure mode on this end, and here's the failure mode on this end. It's basically that the classifiers are too simple. When the classifiers are very simple, they don't suffer from that problem anymore. The variance here is low, right? They're too simple to memorize the data set. Right? But on the other hand, they're also too simple to generalize well. And the noise in this case actually is independent of lambda, and I think that's typically the case, right? Because lambda is just a modeling assumption. So the noise is really is a function of the data set. So that's actually constant. I'm estimating it every time. So in some sense, you see how much the estimation varies here, which is roughly also how much this jumps around. Right? So the noise is basically always there, and there's little we can do in this case if we just change the trade-off between regularization, how much we regularize and how much we focus on the loss. And so what you as a data scientist trying to do is you try to find the lowest point here, right? So in some sense actually somewhere here. Right? The point where the variance is low but the bias is not quite large enough to basically mess you up by being too simple. Right? And so you basically want to find the sweet spot in your setting. Any questions? Any questions about this project or this demo? Okay, all right. Let me move on then. Yeah, question.
So if you apply this thinking about the expected error to, for example, the Bayes optimal classifier, you get the lowest error?
Sorry, say that one more time.
If you, let's say the classifier that we use is the Bayes optimal classifier.
Yeah.
You get the lowest error because it seems that this Bayes optimal classifier has some bias.
Right, so the Bayes optimal classifier, can anyone tell me what is the variance and what is the bias of the Bayes optimal classifier? Any ideas? Yeah. So the variance is obviously 0, right? Because the Bayes optimal classifier is, computed based on the distribution, and the distribution, the training set in some sense has nothing to do here, right? So there's no variance across classifiers, there's 0, right? And the bias is how much does the expected classifier differ from the expected label, the prediction of the expected classifier differ from the expected label. Well, that's exactly what you predict with the Bayes optimal classifier. So you also have zero bias, right? So what you're left with is the noise. So the noise is something that even the Bayes optimal classifier gets. Does that make sense? So one more time, variance is basically this, right? H bar. There's the variance, right? The Bayes optimal classifier always outputs the expected classifier. It doesn't use training data. It uses the distribution. So this here is 0, right? Then the bias is the following. The bias is h bar of x minus y bar of x squared, right? The Bayes optimal classifier, what does it do in regression? In regression, you output exactly y bar of x for every single x. That's the output of the Bayes optimal classifier. Right? And you always get exactly that, so that's also 0. So the only thing you're left with is the noise, and the noise has nothing to do with which model you're using. So you're still stuck with that. Yes?
So that noise isn't exactly like which memory you use. So then when we're picking the best memory to use, why do we consider noise in the sum we're trying to measure?
It's just always there. Like,
But if it's there for all languages, then couldn't it add like random stuff to the sum? Then
yeah, but how do you get rid of the noise? You cannot remove it. Right? So empirically, you just observe the error, which is the sum of these 3 terms. Okay, any more questions? All right. So what I want to look at today is basically the setting. Let's just go back to ERM. And so this is the setting that we just saw in the project, where we basically say we want to minimize some parameter w. We have some loss function that we sum over, well, I think we wrote it this way, x comma y, w, plus lambda times some regularizer. And this could, it's typically the L2 norm, for example, something like this, right? And so the first thing I want to basically now depict is the graph that we just saw, what happens when we change our lambda, right? And so I will try to convince you that lambda is actually one way of trading off between 2 different concepts, and we call these underfitting and overfitting. And let me just draw a little, this is very dirty. Let me just draw a little picture. Okay, so we want to look at the error as our lambda changes. And so in the project, we looked at the test error and the 3 different terms. Let us for now just look at the test error and at the training error. Right? And so as lambda becomes large, and this here is the error. Right? So as lambda becomes large, if lambda is very, very small, right, then basically we're putting all our weight. So here's our loss function, right? So assume lambda is 0. If lambda is 0, then this optimization has no weight on the regularizer, and the only thing we are trying to optimize is the loss on the training data set, right? So this means the training error must be very, very low, right? Because we're not doing anything else but minimizing the training error. And as lambda gets larger, if lambda is really, really large, what happens? Then this term is completely dominated by trying to find a simple solution. Right? In the extreme case, you have an all 0 vector. Well, the all 0 vector is basically as good as random guessing. And so your training error will be really high. Right? So your training error basically looks like this. It's not linear. Let me draw this again. Maybe more like this. Okay, this here is my training error. And my testing error, well, here are the 2 things. So clearly, if my lambda is really, really large and I return the all 0 vector, my testing error will also be really large because I just returned a bogus classifier. If my lambda is really, really small, then the problem is I'm just minimizing the error on the training data set and I'm focusing too much on the training data set. And so what I get is the following. Right? I basically get a decomposition like this. Right? So this here is my test error. And this is exactly what you will observe in the project, and what we just saw, that basically as my lambda is too small, the test error is high, then there's the sweet spot in the middle, and then if it becomes too large, you're over-regularizing, and the test error goes up again. Whereas the training error only goes up as you regularize more. And we call this regime here overfitting, and this here underfitting. And so what's basically happening here is, if you look at the bias variance, you would have to draw the bias variance curves, then basically in this regime here, the variance is really high, and it goes down. This is the variance. And the bias goes up. This is the bias. And so the noise in this case is just constant, so we don't have to look at this. And so the question is, how do we find this sweet spot? Sweet spot. Okay, any questions about this? Yeah?
So does it only apply to the regularizers that are correct, or does it have to
Does it only apply to which regularizer?
So like regularizers that have, correct tires.
Oh, I see. Yeah, this is generally, I see what you're saying. So this is generally applies, but if you have the wrong regularizer, you are increasing bias more, I presume. Yes. Yeah. So, so the question is, what happens if you make the wrong assumption about the regularizer? So, for example, you can have Gaussian noise, then you get the L2 regularizer, and so on. And the curves look similar, but you can actually get affected by how quickly the bias here rises. Yeah, it's a good question, very good question. Any other questions? Okay, good. So we call lambda here is the hyperparameter of our model, and that basically balances this trade-off. And so how do you find the best lambda? And typically, Actually, let me just characterize these two a little bit more. So overfitting, I think we already talked about. Overfitting is where variance is high. That basically means we're memorizing aspects of the training data set that are too specific, right? So, the example would be, I take images of let's say, students and faculty or something, but it turns out that students are disproportionately more often, the pictures just happen to be in front of trees or something, and faculty tend to, there's fewer pictures in front of trees, more in front of buildings. That's a total coincidence, but the classifier would pick up on it just because it happens to be true in this data set, but it does not generalize, right? So these are kind of the things that basically happen. In this case, the training error is very, very low, but that does not translate to the general setting. In the underfitting setting, what happens is that your classifier is even bad on the training data set. Right? So that's the key part here. That I give it certain data sets, data points, and even those that it has seen, it can't do correctly. Right? And that's because, for example, in terms of over-regularization, my classifier is constrained to be on a small ball, and it just doesn't have the expressive power to even get every single training point right. Okay, so how do you find the sweet spot lambda here? And the simplest thing that people use is called cross-validation, or k-fold cross-validation. And it's quite simple. Basically what you do, and it's also called grid search, actually. So there's two different things. So grid search and k-fold cross-validation. And so the first thing is grid charts, and this is really, really simple. So here's what you do. You just say, well, which lambda is good? Here's what I do. I just take my training data set, I split it up into training and validation, and then I just try out a whole bunch of different values of lambda, and for each one of them I record the error I get, and then I pick the lowest one, and I say the lowest one is reached here, and that's the lambda I pick. All right, so each one of you would have invented this, and you would be famous, right, if you'd done it 40 years ago. But unfortunately, it's too late at this point. But so it's a very simple process, right? So you try out all the different values of lambda, evaluate the classifier on the validation set, and pick the lowest one. Ideally, you want to try as many different points of lambda as you can, different values of lambda as you can. The problem usually is that it takes a lot of time to train the classifiers. You have to find some trade-off. One thing that people do is they do telescopic search. So telescopic search is basically, first you have very gross setting of what the right lambda is. Then once you pick the best one, and typically this can be order of magnitude. So you do this on a logarithmic scale. So you try out lambda equals 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, and so on, to the 10 to the 5 or something, right? So you try out the different orders of magnitude just to get an idea of what's the right regime of your lambda. Then you pick the best one. Let's say in this case it's the best one here. Then once again you try out 10 versions of lambda, but just around here. And then you pick the best one, which may be here, for example. All right, so there's a two-step telescopic search. So first you look at where should I search, and then you zoom in that regime of the hyperparameter axis. Any questions about this? Okay, so it's really simple. There's one danger. And the danger is if you try out many, many different values of lambda, what is going to happen is that you will inadvertently overfit over the validation set. Right? And that is problematic. Right? So what will actually happen? Some lambdas may work better just on this particular validation data set, just because it only contains a couple hundred points, right? And you have to be careful, right? Of those 100 points, maybe you only get 5 wrong, right? So if you get one more wrong, right, that increases your error from 5 to 6%, but it's only one data point that's now more wrong, right? So is that really something you want to, rely on, right? So you have to be very careful, right? So if your validation set is too small, you may actually very easily make erratic decisions that basically, give you a lower error on the validation, but again, it doesn't generalize to the true testing. Yeah?
That still happens if you combine telescopic search and k-fold cross-validation.
So that's, all right, good. So that's exactly what I'm leading to. So the answer for this is k-fold cross-validation. And so k-fold cross-validation, what you do here is you say, well, I don't just pick one validation set. Actually, every single data point in my data set should be a validation point. And so here's what you do. You basically don't just make one split, you make many splits. So basically what you do is you divide your data set into k different buckets. And you say k minus one of them are used for training, and one is used for validation. And I can do this exactly k times, right? I can always leave out another bucket. So, the first time I leave out this bucket here, then I train classifier here, evaluate it here. Then I leave out this bucket here. I train a classifier on all the others and evaluate it here. Okay? So now for every single lambda, I don't just get one error, one validation error, I get k validation errors. And the beauty about this is that A, it's much, much more accurate, and B, I also get standard deviations, right? So I know how much this actually varied across the different validation data sets, okay? So that can tell me if one point is a little better than the other, but that's well within the noise that I see anyway. It doesn't make any difference. Any questions about this? Yeah?
So the validation acting as our actual test set, or we actually have separate tests?
So the test set is the one you only touch once. And that's basically what you report to your boss. And that's the true estimate of the error. Yeah. What you then do after your boss approves it, you train one more time, where you stick in the test set and you don't tell anyone, right? And then that's the final classifier you push out, and that actually does a little bit better because there's a little more data, right? And that's okay, as long as you never use that test set again. Yeah. How do you choose K? Good question. K stands actually for Kilian, and larger is better. Now, the larger K, the more buckets you have, the better is your estimate of validation. The problem is the slower it is. So typically, what you want to do is in some sense a trade-off of how much time, how exactly accurate you want to find the best lambda. In some sense, how much does your boss pay you in a bonus, when you actually get the lowest possible error. That's in some sense what it is. So how much do you really care about it? It also depends on how big your data set is. So one thing is, in the extreme case, k equals n. So in this, that's the same thing as it's called leave one out cross-validation. So in this case, actually, you basically you run it n times, and you only leave one point out. And you just see, do I get it right or do I get it wrong? But because you average over all n times, you actually get a very accurate estimate of the error. The only problem is it's really, really slow if n is large. That's, however, often used when your data set is small. Right? So, for example, I've worked with medical images, and there each image, it's MRI scans of people's skulls and brains. Each one of these cost several $1,000s, so we could only afford, maybe 11, right? So what we did is we trained on 10 and left one out, and we did this exactly 11 times. And that basically then gives us, this is basically our cross-validation in this case. But very good question. Any other questions? All right, awesome. So, so one way to regulate overfitting is regularization. Another one that's also very, very common is early stopping. And so early stopping is something that basically, this is exactly what you think it does. It basically is a part of your optimization process. So when you try to find your parameter vector W, you basically don't optimize all the way to the end, you just stop early. So for example, let's say you do gradient descent, right? So one thing, typically the way we described it is you keep doing gradient descent, you keep improving it until your loss basically doesn't change anymore. That's totally fine. But one thing you could do is you could just stop early, right? And return basically some suboptimal result. And turns out there's a very deep connection between regularization and early stopping. And in some sense, it's actually quite similar. Can anyone think about why that is? Maybe I give you a minute to discuss that with your neighbor. So what's the deep connection between regularization and early stopping. So think about logistic regression or something. Okay, any suggestions? What is the connection? Yeah? That's exactly right. So in some, in both cases, basically we control how much we minimize the loss function, right? And one is basically we stop it at the edge of a ball, right, of an L2 ball, and so you can't go any further, right? That's the regularization point of view. So we can view it as this thing here. We start with some W around here. This here is our loss function we're trying to minimize. We're trying to get to this bottom here. In regularization, we basically put a glass ball around here. And our minimizer moves down but hits the glass ball and can't get out of here, right? That's basically the regularization basically says you have to stay within a ball of some radius, whereas early stopping basically says you move, and eventually you stop, right? Or another way of looking at it is if you basically, if you would only take 0 gradient steps, right? And let's say you start with the O0 vector, which you typically do with loss functions. Then you actually get a vector with 0 norm, right? And as you keep adding gradients to it, right? Like the first time what do you do the first time, right? You say W becomes W, minus alpha times G, but alpha is a very, very small number. That's the 0 vector initially. So now you add a vector times some very small constant. So the norm is tiny at the beginning, right? Because alpha is tiny. Does that make sense? So after one step, you still must have a very small norm, right? So if you would take the norm of this, you could take the alpha out of the norm. Alpha is a very, very small number, so the norm must be very small, right? So you need, as you basically do gradient descent for more and more iterations, slowly your norm can grow, okay? And the regularization, you're basically saying, I just put a cap on the norm, right? So there's a very, very clear relationship between these two. And so basically however, the x-axis is in some sense inverted. So more iterations means less regularization. So the way it works is the test error looks the same, but actually the training error looks like this, right? So this here is the training, and this here is the test. So as we keep going, we will more, make fewer and fewer mistakes, because that's exactly what we're minimizing with our loss function, right? But at some point, at the beginning, what we are fitting generalizes to the test point, but at some point we will start, learning things that really don't generalize anymore, and then we're overfitting, and then we move up, right? Also, if you think about it in terms of variance, right? If you had two different data sets, right? What would that look like? If you have two different data sets, the loss function would look a little different, right? So let's say this is my data set 1, this here is my data set 2, right? So they have slightly different minimas, okay? This would be actually an extreme case. But what happens at the beginning? At the beginning, we kind of, we're moving up in this general direction. So at the beginning, the variance is very small. If I just take a few steps of gradient descent, my parameters won't vary very much, because they're all going in this direction where the minimas are. Okay, does that make sense? Whereas as I keep iterating and I'm minimizing my loss more and more, eventually, I'm going down to exactly the minimum of this particular loss function of this particular data set, right? And I'm not ending up at this minimum, which would be a different training set, right? So as I'm minimizing more, the variance between these points becomes larger, okay? Because I'm getting more and more directly into the minimum that really only is the minimum for this particular data set. And a different data set, actually, this may be actually not a great solution. Okay, does that make sense? Raise your hand if that makes sense. Okay, awesome. Okay, terrific. I will see you all on Monday.